Hi, my name is Jake, and this is Alex. Our presentation will cover the blockchain use for security.
Blockchain is a groundbreaking technology which found its beginnings in 1982 when the cryptographer David Chaum proposed a blockchain like protocol for cryptographically secure systems. Blockchain proposed decentralizing data and storage and was notable for its immutability. One man, Satoshi Nakamoto, later improved the design of blockchain by adding things like timestamp blocks and signatures. Nowadays, researchers are devising best practice use cases for blockchain technology. Not all technologies demand blockchain technology. However, it truly shines in its approach to decentralization. Next slide, please.
And going more into that in terms of security, we first have to understand how the CIA triad applies to this blockchaining technology. So first off, coming into confidentiality. When it comes to confidentiality on the blockchain system, we'd simply put by hiding the transaction information from the unauthorized individuals on the system, although it can be difficult when the system is public. These important points must be taken into account to see how to counteract the public aspect of the blockchaining system. So, when is it each instance viewable on the and how much information can be seen? If the person is a regulator or just a underling, has been assigned to the right accessed information, and if the network is flexible or static. These show that the important points of confidentiality because of the peers and if they are who they say they are. Moving into integrity, while it is good to apply encryption on all data, this is only good for confidentiality on internal attacks and not corruption. Blockchain uses cryptographic hashing to ensure that the ledger remains tamper-proof. For example, when you commit something to a peer to the Hyperledger, it will always validate that the new information on the block. If the peer is hacked, only that block will be affected. And then moving into the availability, and then also SHA-256 uses the same type of hashing function. So in terms of availability, blockchaining will always use its value on the system unless that block is being manipulated or broken. That will always be kept. The face of blockchaining system is ran on a decentralized app or a DApp. This keeps the front end and the back end of the system on the same loop and makes sure that the availability of the blockchain is open at all times, making sure it's available to everyone at all times.
So, we wanted to address the problem with centralization. First of all, there is no fault tolerance with centralization. When network duties are given to a centralized authority, there is little room for redundancy support. Copies of data can be made and backups can be instated, but server stoppages could easily take down a network. And the main goal of many organizations is to maintain system uptime and tolerance of network outages. As for trust of central authority, certain implementations which use central authority don't account for many threats. Trust in a central authority creates internal vulnerabilities such as user error, user misuse, and user malignancy. Finally, lack of consensus. Although a copy of an image, such as a log or a database, might be saved on a central repository, there is usually no other entity to confirm the true state of that image. Next slide, please. So we propose the blockchain solution. With fault tolerance, blockchain technology is fault tolerant due to confirmation and verification of state by every block within the blockchain. The blockchain can operate completely decentralized and does not require trust in a single authority. Distributed systems use algorithms, such as proof of work, to come to a consensus on the state of the data in the blockchain, and this renders them highly resilient to malicious attacks, even when a significant portion of the participants are malicious. Next slide, please.
So our first ideas of implementation were going over a PKI or a public key infrastructure, so that we can apply security, also attaching onto a two-factor authentications. So with the use of PKI, there are many problems that our group faced when trying to implement to our blockchain security. Using only one resource to pursue PKI implementation of security proved difficult, and the addition of a CA did not help. With the idea of two-factor authentication, we cannot decide on the right way of pursuing the security and in collaboration of our team. So with these limitations in place, both of our implementations were incomplete and cannot be accurately used to convey security.
Similar with Jake's PKI implementation, I only had one resource which I was using for my two-factor authentication implementation, which didn't leave much room for growth. In addition, there was slow confirmation time on the blockchain for the 2FA implementation, and this rendered the implementation unusable for real-life applications. In addition, if I were to expand this implementation, the level of difficulty wouldn't have really complied with our project timeline. Next slide, please.
So we had to create some new objectives. The main objective that we wanted to cover during our research system implementation is ensuring that confidentiality, integrity, and availability are going to be secure on medical record storage program. This program using blockchaining technology. And then this moving into what research we found on confidentiality. To quote the National Institute of Standard and Technology, blockchains are tamper-evident and resilient digital ledgers implemented in a distributed fashion and usually without a central authority. This is then enforced of privacy or an enforcement of privacy, which can be described as security or confidentiality. Monitoring communications on nodes is key to finding errors on the system, which would lead us to privacy protection. A technique explained above, using nodes to monitor peer-to-peer transactions, can be used to track all individuals and break confidentiality. Thus, it is important to establish who you are working with and if they are who they say they are. I would recommend using a trapdoor to establish if the person is using the right node and if they are who they say they are.
So initial methods for integrity, or what we currently use, include checking hash values via message authentication code algorithms, aka a MAC. However, these implementations can be computationally heavy and they consume a lot of bandwidth when there's a lot of transactions on the system. Another solution for integrity is using a third-party auditor to confirm file integrity. However, as we have addressed before, this requires a third party, which means centralization, and we've already addressed that centralization is not good. And the channel that happens due to the third party causes that channel to be vulnerable to man-in-the-middle attacks. Next slide, please. The current blockchain solutions for integrity contain history of ownership. And when a new transaction is created, modified, or deleted, the blockchain will be notified because it stores the current hash and the previous hash of the transaction. The server can monitor all of that activity that occurs on the blockchain. If an unauthorized change is made, the server can be notified of that change via an API. One solution that uses this methodology is Abraxas. They contain metadata such as transaction types, timestamps, and signatures, which notify the operating system when a change has been made in the file system. Next slide, please.
All right, then leading into the final part of the CIA triad of research on the availability, the use of a decentralized app, or the DApp as we called it, on the system is paramount to make sure that the front end and the back end of the system are working together. This can be completed through transaction comments by both peers on that system. So the way this is done is through smart contracts, which can be used to make sure that the system can be run by anybody using that system. Ethereum specifically has a system put in place so that the transactions can be viewed through newly mined blocks. It is also done through two user-defined parameters. This would be gas price and gas limit. Both of these are used along with network delays to monitor if it is slowing down the network or if it is not. And what ultimately boils down to is that the fewer nodes that are shown to be on the blockchaining system, the more likely it is to be slowed down on the system. So the bigger the better, the smaller the worse it gets.
And going off of what Jake mentioned with smart contracts, we did decide to implement smart contracts for our project. And the resources that we used to do this were hardware such as laptop and a desktop computer, but the meat and potatoes of our project resources comes from our software and our programming software. So I used Visual Studio Code to run all of the programs. I learned how to program in Solidity from a game called Crypto Zombies, and I used Ganache, which is an Ethereum simulator that makes developing Ethereum applications faster and easier. The programming languages I used, obviously Solidity for creating the Ethereum smart contracts, Web3.js to connect to the blockchain, and Python for deploying the smart contracts to the blockchain. Looking at our implementation is meant to simulate a patient sending their data over the blockchain to their doctor. The patient's data and identity would be secure, but the doctor could hypothetically receive the patient's medical records through an API call, while evidence of the transaction would be stored on the blockchain. Looking at our deploy.py program, where we create the transaction on the blockchain, our first step is to build a transaction. We do this by calling the smart contracts constructor to initialize variables such as the gas price for sending the transaction, the chain ID, and the address which the transaction is from. And finally, the nonce, which is used for hashing the metadata of the transaction. We then sign the transaction digitally with our private key. Finally, we send the transaction to the blockchain. Then the transaction receipt is proof that our transaction was signed. Moving on to records storage.sol, our Solidity code, we can see the main logic of our smart contract. We created a struct which contains patient data, and that is declared as an array of structs to store our information. Later, we'll use these mappings, which are key value pairs, for looking up the information. One red flag you might immediately notice when looking at our functions is that all of them are public. This is simply so that we can call the functions from within our program for this implementation demo. However, it is good practice to mark functions as private by default. When a function is private in a smart contract, the only other functions within the contract will be able to call it, so any functions from outside in another contract wouldn't be able to access those private functions. Not even functions that inherit from the contract can use these functions. In addition, we could use Solidity's message.sender attribute to refer to the patients on the blockchain. Message.sender provides security because the only way someone could modify someone else's data would be by stealing their private key. Let's run our program to see how it works. As you can see, the contract gets deployed, the data gets updated, and this is simply using these retrieve functions to call that data, which is possible because they're public. Taking a look at our Ganache blockchain simulator after running that program, we can check the recent transactions and see contract calls and creations. Looking further into the contract call and the creation, we can see that all the data is hashed and no data is revealed. In a usual blockchain implementation, we would simply be recording the fact that the events occurred, and we wouldn't be storing any data on the blockchain. But for now, our main measure of securing confidentiality is by using a nonce to hash the metadata, which produces pseudo-randomness. And the fact that anonymous addresses will protect the identity of patients it is another aspect of our confidentiality, because no associations can be made between patients and their data. Moving on to integrity of our implementation, like Jake said, the blockchain is tamper evident, which makes it obvious when data has been corrupted or altered. However, verified blocks on the blockchain are immutable and resilient to all types of manipulation. Finally, in availability of our implementation, we provide high tolerance and serviceability because all of the nodes in our blockchain have a copy of the blockchain with every recorded transaction.
All right, so this is our team information on what both of us contributed to our implementation and research of the subject of blockchaining on security. We thank you for listening in on our presentation.
Thank you.